So far for integration, we've learned like 12 different forms that we can take integrals. U to the nth du, e to the u du, du over u. Altogether there was 12 of those. So just like with derivatives, we learned some formulas, but with derivatives, we had the product rule and the quotient rule and the chain rule, which helped us do so many other things. Unfortunately, with integration, there is no product rule. But the closest thing we can come to a product rule is something called integration by parts. That is often done if you get an integral that has one function times another function. So, in order to do it, I'll try to get you a proof for this. So we're going to start with the derivative of the product rule. So if we take the derivative of a function f of x times g of x, we know the rule is the first function times the derivative of the second function plus the second function times the derivative of the first function. Well, if that's a true statement, what would happen if we came along and took the antiderivative of both sides? You should get the same answer. I'm going to take the antiderivative of that side and now the antiderivative of this side, which I can split up into two antiderivatives. And say I wanted to now solve for, split these two up, and say I just want to solve for this first circled part here. I can say the integral of f of x g prime of x dx equals, and then I've got this side over here. Well, what is the antiderivative of the derivative? It's just the function. So it's just going to be f of x g of x. And then I now have to bring this to the other side, so it's minus the integral of g of x f prime of x dx. And that is the formula for integration by parts. Now, it does look kind of complicated. So sometimes to make it easier, we let u equals f of x and dv equals g prime of x dx. So du is f prime of x dx, and v is g of x. So if you write those two things, if you let u be f of x and v be g of x, we can write this u times v. And this is the integral of u, and g prime of x dx is dv. And then we have minus the integral of g of x, which is v, and f prime of x dx is du. So this is probably the most common way that people remember integration by parts. The thing that makes this seem like not such a good formula is you're starting with an integral, and in order to do it, you have to do an integral and something else. So it almost seems harder. So obviously, this isn't always a good thing. It's only a good thing if this integral is easier to take than this integral. So you have to be smart about the way you set these things up to make sure that that integral is easier. Now, besides deriving that, I think the best thing to do is just to go into an example and show what you would do. So, here we have a function times a function. That's when we have to consider that maybe integration by parts would be a good idea. And as soon as we do that, we know we're going to need a u and a dv to be what these are. But you have to be smart about which one to pick. Well, normally, you'd want to pick an x here because when you take the derivative, it actually gets simpler. Unfortunately, we have not learned the antiderivative of the natural log of x. So we have no choice but to put the natural log of x over here and along with the dx, because what we're going to have to do on this side is we're going to have to take the antiderivative of that. So the antiderivative, I'm sorry, we just decided we couldn't do that. So we're going to put, on this side, we're going to put the x dx. The reason we're doing that is because on this side, we're going to have to take the antiderivative, and we can't take the antiderivative of the natural log of x. We can take the derivative. It's 1 over x. So the differential du is 1 over x dx. The antiderivative of x dx is x squared over 2. So now we can use the formula and see if it works. Maybe it won't work and maybe it will. So we know the integral of u dv, which is what we've got, is uv. Well, this is u and this is v. It's on the diagonal. So we get x squared over 2 times the natural log of x minus the integral of v du. That's the second part. Well, when you multiply these together, you get x over 2. So did we succeed? Is this integral easier to take than what we started? And I think the obvious answer is yes. So what is it? It's x squared over 4 plus c. And we're done. We came and we started with a difficult integral. With a little manipulation and using this formula, we came up with a simpler integral to do. And so we got an answer. So that one worked out nicely. Well, let's try another one. Is it possible that this could be integration by parts? Well, it's a function times a function. So that's a good indication that it might work. So let's pick our u and our dv. So in this case, we can take the derivative or the antiderivative of either one of these, but we're trying to make our life simpler. So this time we really are going to put the x squared here and the cosine of x on this side. So du is 2x dx, and the antiderivative of the cosine is the sine. So if we use our formula up here, we get uv, so on the diagonal, x squared sine of x, and then minus the integral of 2x sine of x dx. Well, not as good as the previous one. This was a really easy integral to take. This one I'm not so sure. But it is a function times a function. So maybe I can do parts a second time. And you have some confidence because now you just have x to the first power instead of x to the second power. So let's try it again. Let's let u equal 2x and dv be the sine of x dx. So du is just equal to 2 dx, and v is equal to the antiderivative of the sine, which is minus the cosine. So our answer is going to be, don't forget, that's still there, minus, and now we do, for this integral right here, that's why I put that parentheses, because I have to subtract the whole answer to that. So I go uv, so it's minus 2x cosine of x, and then minus, so minus times a minus is a plus, the integral of 2 cosine of x dx. So all together, minus times minus is plus 2x cosine of x, and now we finally got an integral that's easy. The antiderivative of the cosine of x is the sine of x. And then it's an indefinite integral, so we have our plus c. So here was just a case where we did integration by parts, but we had to do it twice. We first made it a little simpler, and then we made it even more simple that we could just take the antiderivative with our formula. Okay, try this one. U is one function, it's a function times a function, so it very well could be that parts is going to work. Now I'll tell you right now, we know how to take the derivatives and the antiderivatives of both of those without too much trouble. So it really doesn't matter which way we go. Either way would work out. So I'm going to pick e to the x and sine of x. So du is, the derivative of e to the x is e to the x. This is minus the cosine of x. So our formula says u times v, and then minus the integral of v du. So that minus times minus is plus the integral of e to the x cosine of x dx. And look at, we're kind of in the same shape that we started, but let's try it. Let's let u equal e to the x and dv be the cosine of x, just to see if it's going to work out. Du is e to the x dx, and v is the antiderivative of the cosine. So you get e to the x times the sine of x minus the integral of e to the x sine of x dx. And then you might as well bring this down. And your thought is, oh boy, did I mess up? Because I'm back to where I started from. But remember, this is what you started from. So all of this is equal to this. So I can say the integral of e to the x sine of x equals all of this. So there's no reason I can't, since that's a minus, I can bring it to the other side and then have two of these. Equal to what's left. Minus e to the x cosine of x plus e to the x sine of x. So the last step to get what we wanted is just to divide by 2 and add your c, and then that's done. So again, we ended up having to do it twice. And it looked like maybe we weren't getting anywhere and we were going to get into a circle, but remember, since that's a minus, you can combine it over here on this side. Okay, so let's proceed to a couple more. Well, the first look at number 4 is saying, oh, this is not a function times a function. But it is something that we learned how to take the derivative of, the inverse sine of x, but we never learned how to take the antiderivative. Well, when you have a case like that, you can also use integration by parts. You just have to say the other function, I'm always allowed to multiply by 1. And 1 is a function. F of x equals 1. So I'm going to let u dv. And since we don't know the antiderivative, that's what we're trying to find, we have to put that on this side and then the 1 on the other side. So, do we remember? It wasn't too long ago that we learned the derivative of the inverse sign. It was 1 over the square root of 1 minus x squared dx, and the antiderivative of 1 is just x. So we get x times the inverse sine of x, and then minus the integral of v du. So we get x over the square root of 1 minus x squared dx. Well, did we succeed? Do we have an integral that we can do now? Well, I think you could. Can we get it into one of those 12 forms? I'm thinking of u to the nth du, where n is negative 1/2. So I could let u equals 1 minus x squared and do my du is minus 2x dx and do a u substitution. And there's nothing at all wrong with that. But I'm going to show you something that I usually teach students at this point in time, is to maybe we can wean ourselves off of that u substitution. So what I'm going to do is rewrite this as 1 minus x squared to the negative 1/2 times x dx. And see, is this in the form of u to the negative 1/2 du? Well, not exactly. The derivative of this, the du, would be minus 2x dx. So what we're going to do is put that in there. Now, in order to keep things okay, if we put that in there, we also have to multiply by negative 1/2. So I can do that out front. Now, it is in the form of u to the nth du. So the antiderivative is u to the positive 1/2, and then divided by 1/2, which wipes out this, plus c. And that's our answer. X inverse sine of x plus the square root of 1 minus x squared plus c. So back when we did the talk on inverse trigonometric functions, we found the derivative. We never found the antiderivative. There it is. Maybe that's why we don't memorize that, because it's so complicated. Just know, if you ever need it, you can do integration by parts. And that happens when you know the derivative but don't know the antiderivative. Okay, so let's go to finding an area between the natural log of x and the x-axis between 1 and e. So little sketch is good. The natural log of 1 is 0, and the natural log of e is 1, and we know the natural log function goes down here. But between 1 and e, this is the area that we're looking for. So with all area problems, we have to make our rectangle. And I think it makes sense to make it up and down because it's already solved for y. So the area is going to be the integral from 1 to e of the height times the width. And the width is dx. So that's the setup for it. But do we know the antiderivative of the natural log of x? We think back. No, we never learned that. But we do know its derivative. So maybe I can use the same idea I did up here. I know the derivative, so I'm going to let u be the natural log of x, and dv be just 1 dx. So du is 1 over x dx, and v is just x. So when I use integration by parts, I get uv x natural log of x minus the integral of v du. Well, x times 1 over x is just 1. So you get x natural log of x minus x. And if this was an indefinite integral, you would have found now the antiderivative of the natural log of x. But this is a definite integral. So you have to go from 1 to e. So you get e times the natural log of e. Well, the natural log of e is 1 minus e. And then the other side, you get 1 times the natural log of 1. The natural log of 1 is 0 minus 1. So altogether you get 0 minus a negative 1, or 1. So there's 1 square unit in there. So basically, that's 1 square unit. This is also 1 square unit. Okay, so now that we've done an area, let's do a volume of revolution. We haven't done one of those in a while. So find the area between y equals e to the minus x and the x-axis between 0 and 1. Well, e to the 0 is 1, and e to the negative 1, 1 over e is a positive number, but it's less. Function e to the minus x goes down like this. But we're only looking for the area between 0 and 1. And now we're going to revolve this area around the y-axis, forming a three-dimensional solid. Remember, what's the best way to make the rectangle? That has to be your first thought. The best way to make the rectangle is up and down, because it's already solved for y. But since now we see that the rectangle is parallel to the axis we're rotating, it's going to make a shell. So the formula for shells was, the volume is 2 pi times the integral, and we're going from 0 to 1, and there were 2 things we needed with the shell. We needed the height of the shell, which is e to the minus x, and then we needed the radius from the axis. Well, the distance from the y-axis over is always called x. So this is just going to be x. And that is the setup to get our volume. And what do we notice? We have a function times a function. So maybe integration by parts is going to work. So let u equals x so that I can make things simpler. The derivative of x is just 1. And let dv be e to the minus x dx. And the antiderivative of e to the minus x is e to the minus x divided by a negative 1. So if I use my formula, I get minus x e to the minus x, u times v, and then minus the integral of v du. Well, minus times minus makes it plus the integral of e to the minus x dx. And I have to remember that I'm still going from 0 to 1, and I still have the 2 pi. So I don't want to forget that, so I'm just going to write it over here. But I'm first going to find out what this is. The antiderivative of e to the minus x is minus e to the minus x. So now I can take that whole thing from 0 to 1, and I didn't forget the 2 pi. So now I just plug in 1, and I get negative 1 e to the minus 1. And then I get minus e to the minus 1. And then when I plug in 0, I get 0 minus e to the 0. So all together, what's my answer? 2 pi minus times minus would be 1, and then you get minus 2 over e. That's your volume. And just to kind of check, it is a positive number because 2 over e is less than 1. So that's a little bit of a review of something that we haven't done in a while, volumes of revolution and finding areas. They're still going to be very important. So one last one. What if we get the integral of x to the 4th e to the x? Well, let's try u to be x to the 4th. I'm going to go through this pretty quickly. du is 4x cubed dx. V is the antiderivative of e to the x is e to the x. So you get u v minus the integral of v du. And then you're going to do it again. You're going to let u equals 4x cubed and dv be e to the x. But you kind of see that this is going to take a long time. So there's just something I'm going to show you that sometimes can save you some time. It's called the tabular method. And it works if one of the functions happens to be x to a power, and especially if that power is pretty big. And you can see it's going to take quite a few steps of integration by parts in order to solve this. Because integration by parts has a pattern to it, we can go like this. We can take x to the 4th and put it on this side, and e to the x on this side, and then we just start taking derivatives on this side and antiderivatives on this side. So 4x cubed, 12x squared, 24x, 24, 0. And then this is going to be pretty easy. E to the x, e to the x, e to the x, e to the x. These are all my antiderivatives. So now, how do you get your answer? What was the beginning of the answer here? It was u times v. It was on this diagonal right there. So that's going to be the first part of my answer, x to the 4th e to the x. And then what do? Now we take the integral of this times this. Well, they're right here. So what's the first part of the answer? The first part of the answer is going to be, again, on the diagonal. The trouble is, the formula says minus that integral. So we have to put a little minus sign in front of there. So we go minus 4x cubed e to the x. And now we would take, when we do that, Pants, now you'd have to take Pants on 12x squared e to the x. Well, where would the diagonal answer be? The diagonal answer would be right here. But we've got that minus sign. but we have now had two minus signs, so this one's going to be back to plus again. So I go plus 12x squared e to the x. And then you just keep continuing. Now that's going to be minus, so you get minus 24x e to the x. This is going to be back to plus again, so you get plus 24 e to the x. And then you've run out. Anything else is going to be zeros now. So you're done. You just add your plus c. And this tabular method just saves you time, because now instead of doing integration by parts 4 times, we just did it in this table. So it's just kind of a nice trick. I actually like this way better because you're really using the formula, but obviously this does save time. So that's the tabular method to do integration by parts, and it only works if you have one of the functions being x to a power. So anyway, now we don't have something quite as powerful as a product rule for taking derivatives, because that works on any two functions, but at least we found quite a few where it works here. So good, thank you.